what's going on at WiNDC. It's a chance for us to share with you sort of what we've done in the past year. We had our board meeting just concluded right now, where we had a chance to sort of share ideas about how to move forward, and a number of very good ideas came out of that. So you'll be hearing, we're putting out announcements, and most likely we'll have be organizing a one-day session in September, October for presentations of papers, with the idea of moving toward a submission of a volume proposal to GJEA on applications of WiNDC. Another idea that came out was to organize a virtual summer school event in a couple of months from now, where we have a chance for PhD students who want to learn about modeling to sort of jump in and learn about WiNDC, and we'd also leverage that as an opportunity for the students who would like to participate and then write a paper. We perhaps provide an incentive for them to do that, where we basically solicit paper sample applications from a range of things that could go on the website. So that's pretty good. And then the third thing is that there's a lot of enthusiasm for pushing forward on sort of the international dimensions of merging WiNDC within GTAP. There's a proposal from USDA. We have interest expressed. We've had feelers from different groups. So the idea is to move forward with that. And I'm hoping we can make an announcement. A number of you potentially could be interested in that. So the idea is to do this sort of as an open source exercise, where we have some sessions online to have a chance to sort of have discussions about choices and data sources and so forth. So those are the sort of the things that I immediately off sort of the top of my head that I take away from the meeting. Useful. So thank you for those who are on the board to proposing it. So today we have sort of 2 talks. So the 3 talks are, maybe we could mute. You might want to. Can you mute?
I'll take a mute.
Yeah. So then we can mute. If you just have to unmute yourself, if you want to give a talk, present things. But there'll be three talks today. So Andrew Schreiber will talk a little bit about the work we've done on disaggregation of household data within the WiNDC framework. So this is something we've spent a fair amount of time on. We're really sort of encouraged by how this has gone, and it's going to be coordinated with the release of WiNDC version 3. We've already released a pre-version of that to members of the advisory board, but we'll be opening that up for public consumption within the next month. Following that, I'm very happy to have David Anthoff here from Berkeley. He's going to talk about, I asked him to give some talk in general about Julia Jump, this open source modeling alternative to GAMS, and he's one of the guys who's really jumped on the use of PATH within this framework, which PATH is the solver a lot of us use for doing nonlinear equations and complementarity problems. And so I'll show us a little bit about that. And then he has a student who's working on a version of MPSGE that goes inside of Julia Jump. So we'll talk a little bit about that. It's a nascent project, but it's intriguing to us, because really within WiNDC, I'd say that probably most of our success in terms of our agility at working with data sets is their ability to manipulate models quickly. And this rapid prototyping that MPSGE gives you is really what we lean on for the development of data sets. Essentially what it means is, to do the development work, we don't have to write as much code. So essentially you can write down, rather than write the equations down to check the equilibrium conditions, we just throw the stuff in a model and verify the model runs. And we really lean on MPSGE to tell us if something's wrong. So that's the main that's the trick we use for doing rapid data development, is we always are close to a model. We never leave the model. And we can, give me an idea for a model, I can build the model in 5 minutes. It's like it's all about the speed with which you can adjust stuff. And then finally, we'll conclude. We have this neglected project. MPSGE version 2 is a Ruby script, and I've had to go back at that. I'm going to try to finish that paper in the next. We're going to have a draft of that on the website at some point shortly. And I'll talk a little bit about where MPSGE came from and this new tool that's based on Ruby for translating an MPSGE script into GAMS equations, and whether it's going to take over the existing tool. It's not a matter of efficiency, it's more a matter of complexity. So the main challenge, the code we generate with this tool seems to be pretty fast, because the GAMS function evaluator is fast as an alternative to MPSGE. But The challenge is just that it's kind of complicated. So the number of symbols that gets generated is pretty large. So, but I'll share with you the basic sort of idea. So we'll begin with Andrew. So Andrew Schreiber is his dissertation was sort of the founding, founded the WiNDC project, and we really benefit enormously from having his continued involvement. So we're grateful to EPA for letting him spend some time. And we're also grateful for all the weekends and evenings he spends on this stuff.
Great. So can you guys see my screen?
Yes.
Oh, yikes, one sec. I locked myself out. Okay, there we go. So today I'm going to talk a little bit about the household disaggregation routine that Tom and I have been working on. I'll talk for the first 20-25 minutes, and then Tom will chat about the last couple slides about some of the modeling applications. But most of the talk will be focused about the data work. I'll say that our two names are on this, but there have been a number of people that have been super helpful along the way, and their help's been much appreciated. So we'll give a little overview. Most of the talk will be about the calibration routine, and then we'll highlight some of the modeling applications that we've started to finalize. So in general, the first version of WiNDC featured a state-level data set with a single representative agent by region, which really provided a means to do some spatial distributional analysis, but not within different consumer types within a region. So by income or other sort of characterization of subpopulations. And a key advantage of InPlan has been its disaggregation of these regional consumer demands and incomes by household income groups. And so we began this process thinking about the best way to disaggregate the regional representative agent in this framework. And there's many ways that you could approach this problem, either from the income side or the expenditure side of the income balance constraint here. We approach this from the income side. There's quite a bit of data available on this. And in a lot of our experience, sort of the source side effects tend to dominate a lot of the welfare impacts in these types of models. So getting a good handle about things like wage payments and capital ownership and investment and savings and things was important. We also handle sort of an additional wrinkle here is when we start thinking about breaking up the income balance constraint for the representative agent, we have to start thinking about savings, which is also impacted if we want to run a static versus a steady state model. And so we provide some tools that allow a recalibration of the static input-output tables to accommodate steady state assumptions. And then on the expenditure side, we use income elasticities to separate the demand accounts. So in this work, what we do is we provide two versions of a household data set. One is based on the current population survey, the CPS survey, and the other is based on IRS's statistics of income data, which is different. It's an administrative data set, but it's not a micro data set, or at least the one that we're working with isn't. And so we have sort of two ways about going about this. The interpretation between the two data sets differ, which we'll get into. But what we ultimately find is that you can use a bit of information from both to produce a fairly robust decomposition of the household accounts. So in terms of how we disaggregate the households, we disaggregate them into 5 household types based on income. The breakout will be given later. And then we have a variety of modeling applications. We construct 3 models: a static model, a steady state static model that has an assumption about tracking capital returns, and then we have a transition dynamic model. And within those 3 frameworks, we have 3 different applications. We look at the marginal cost of funds. We have an energy tax example to look at the double dividend. And then we have a sort of a dynamic analysis of COVID. So our original representation in WiNDC 1.0 or 2.0 without the households is really motivated by this equation here. We have sort of, we're limited by the information in the reference input-output tables. The income balance constraint here is consumption plus investment equals wages plus capital plus other. And you know, each component of this limits our ability to do welfare analysis. So for instance, investment here is based on the location of the state level investment demand. So basically the agent making the investment has to live in the same area that's doing that's getting the investment. And then it may not follow sort of, you know, the actual location of the entity doing the investing. You know, wages and capital is sort of the same issue. We require that people living in a region also work in that region, and then people that own the capital in a region that is demanding that capital. And then sort of the other closure parameter here is just all the stuff that can't be explained by those 4 components that are in the input-output table. And so there, you know, there's some obvious issues here when we think about welfare impacts. And so what we do here is we try to produce a better reconciliation of this framework. You know, the original constraint in the previous slide provides a useful control total for wage payments, capital ownership, investment, and things. But using some other data, we're able to sort of shift some of those things around to better represent sort of the world as it is. And so we're able to move towards a better income balance representation listed in this, where we have consumption plus tax payments plus savings equals wages plus capital ownership or interest payments plus transfers. And we're able to break out each of these categories by region and household type. We estimate savings as sort of a closure parameter because we have good information on all the other guys. And then we have some assumptions about where people work and where they live and how capital endowments are consistent with sort of a national closure. So we don't necessarily rely on the capital demands as a measure of capital ownership. And then we break out the other category into cash payment transfers consistent with benefit programs in the US. So the 2 data sets that we use are the CPS and the SOI. I mean, there's a number of differences here, and there's probably too much information in these slides that I'll actually be able to get to. But at a high level, the CPS is a survey data set. The SOI is an administrative data set. That said, you know, the CPS does survey folks that pay income taxes and that don't pay income taxes, and so they, you know, nationally adjusted, they account for more than what's in the SOI data, if we were to believe the survey estimates. You know, we also have microdata in the CPS and the SOI. We have these precompiled state-level statistics. In the CPS, notably, there's no income tax payments, and so we have to augment that part of the data set with some outside information that I'll get to later. But one of the nice features of the CPS is it denominates all major cash transfer payments from government programs, whereas the statistics of income have really limited transfer information and only include those things that are taxed. So what follows, we aggregate households into 5 groups. You know, they roughly correspond with one another. There's a difference here in interpretation. The CPS data is based on census households, whereas SOI data is based on the tax filing unit. So for instance, if there's you know, if there are folks that share an apartment, but they're their own tax filer, then, you know, they're going to be considered separate entries, whereas in CPS, all of those people would be in the same household. And so there's a reshuffling of some of the groups here. And so you can see that in this plot, which plots the share of households or returns by income group, that because it's at the tax filing unit, the SOI data is tilted more towards the bottom of the distribution, whereas the CPS is tilted a little bit more towards the middle or top. So here are the major CPS categories. Both the CPS and the SOI have good data on wages and salaries. The CPS has a little bit more limited information on capital payments. For instance, the SOI has capital gains, whereas this does not. But one of the major advantages here with CPS is that it denominates all the transfers. And so we have really good information about transfer income, which ends up being important for welfare analysis. And then on the expenditure side, there's no tax information. And we proxy savings with retirement income. If we look at those different categories by house, or those different income categories by household category, there's some nice heterogeneity here across the categories. The blue is the lowest income, the green is the highest income group. Wages, the sort of the highest share of wages is for the upper income groups. If we look into some of the transfer information, that tends to be more tilted towards the bottom income groups. And so anyway, this is at the national level, and the same plot can be produced for the state level. It's just sort of a bit more messy, but there's some nice heterogeneity in the data that allows us to capture some of these things. And in terms of the CPS, one of the concerns here is that it's a survey, and so we have to worry about representativeness at the state level. And if you plot out the sort of the observation count by these household categories that we've defined, at least there's some observations for each category across the states. And this looks at the number of observations, and then it's faceted by the year of the data set, which is consistent from year to year. Again, because the CPS is a survey data, there's a healthy literature on underreporting. And so two papers in particular are useful here. Myers et al. Compares the CPS transfer data to administrative totals and reports the share of the total, which is reported in this table here. And then Rothbaum 2015 compares CPS with NIPA accounts and reports sort of the share of total for things not included in the first paper. And so what we do is we use these shares to inflate some of the CPS information to make it more consistent with what's found in the reference WiNDC data that's not disaggregated by household. In order to get tax rates for the CPS data set, we estimate average and marginal tax rates using CPS with TaxSim. And this is all based on Alex Martin's pretty slick code in the SAGE model package. It basically creates representative tax returns and submits them to TaxSim, and you can get tax rates either average or marginal by the household groups. And so we run the TaxSim model for our different income groups and report both of the tax rates. And so these things are included in the database. So on the SOI side, it's similar to the CPS. Again, good wage and salary information. One notable difference is the capital information. There's a lot more here, particularly for capital gains. There's limited transfer information, but again, on the expenditure side, there's great tax information as it's an IRS data set. And so, there are good and bad features across both data sets. And so ultimately, sort of both are used in tandem to try to inform the disaggregation process. And while tax payments are endogenized in the routine, we hold fixed the rates. And so if we compare the TaxSim results in the CPS case versus the average rates that are implied in the SOI data, we get this in the table, and it's actually quite close. There's a little difference between what's defined in each income category in terms of the tax filing unit versus household, but by and large, the labor income taxes line up really well. So on the expenditure side, one idea here at the outset was to try to leverage some additional data like the consumer expenditure survey, which might be something that we look into down the line, but in the first version of this, we end up using income elasticities. that are mapped to the WiNDC sectors. And so these income elasticities are something that we had estimated in the SAGE model package that was referenced in a few slides ago, using the Consumer Expenditure Survey. And so, we have pretty up-to-date estimates here, and we use these things to project how expenditure shares change as income increases. And I'll show some of the results of that later. So the recalibration routine is run for data from 2015 to 2017, again, either based on SOI or CPS. We do it two ways to illustrate a sensitivity in terms of what matters and what doesn't matter. We end up finding that in all of the modeling applications, the results from both data sets really, it doesn't produce very large changes between the two data sets. But in the routine, the CPS-based recalibration is augmented with the SOI capital gains, and then in the SOI case, we augment with transfer totals, because again, it's only SOI includes only information on transfers that are taxable, and most cash payments aren't taxed. So, an overview of the actual routine. We use a four-step process. The first part of it is to solve for the steady state equilibrium investment demand. And this is, if we assume that we want to run a dynamic model, then we have to reconcile the investments in the static input-output tables that don't really think about this when they're being constructed by the DEA with sort of assumptions in the sort of Ramsey style models that have to line up investment with other assumptions on growth rates and interest rates and depreciation. So the next step is we solve an income routine for aggregated regions. Here we use the census region. We find that doing a successive calibration enhances the reliability of the solving. And so we solve this thing at the census region, and then we go down to the state level, enforcing control totals from the previous step in the census region case. And that really helped us pin things down. And then finally, we solve the expenditure routine. And so I talked a little bit about the first step in terms of reconciling the investment. This is important because we estimate the savings for each household. And it turns out that you have to bend the data quite a bit if you don't use net capital demands as opposed to gross capital demands. And so we impose a tax rate on capital demands, and in doing so, it helps the routine quite a bit. So on the income side, when we disaggregate the accounts by the income groups that we were just discussing, we minimize the deviation from either the CPS or SOI data as the objective function. Some of the key highlights here is that we have some assumptions we need to make on wages. We assume that labor market's clear within a census region, and that in the input-output tables, labor demands are inclusive of fringe benefits, whereas in the SOI and CPS data, we just have wages and salary. And so that difference between labor demand and wages is evenly shared across household types as an assumption. So we note that wages, interest payments, and transfers are well controlled. Savings is calculated as a residual of the income balance constraint. And also note that the largest group has much larger totals than what's in the CPS data, but that's largely due to some of the top coding in the survey data and smaller capital payments. And finally, the results match pretty well with small savings with poorer households. And it lines up with other work in the literature that have done similar exercises, but at the national level. So at the state level, one of the important things here, one of the key differences at the state level from the census region level is that we observe that there are many instances in the data where people live and work in different states. For instance, DC is sort of a prime example. I live in Virginia, I work in DC, that we have to accommodate that relationship in the data. And so one of the key innovations we make here is we add a subscript to the labor endowment parameter that we estimate. And so if we think about in the MPSGE code, we have the representative agent by region and household. Their labor endowment is going to be represented by where they live, region R, where they work in region Q, and then the household type H. And then that's summed over Q such that we can match or we can accommodate this difference. And by and large, that matrix is largely populated on the diagonal, but there is a little bit of off diagonal movement to match the data really well. And then on the expenditure side, this is some of the results. We impose the income elasticities. We get sort of the general result that for necessity goods with income elasticities less than 1, the expenditure share is falling as income rises. So for housing, we go from 30% in the first household group to 10% in the fifth household group. The same is for the utilities. For luxury goods, as estimated by the data, like education and hospitals, it's sort of the opposite result, right? You get increasing expenditure shares as your income increases. So, that's a very quick and dirty overview of the routine. There are some additional things that we're thinking about. It's been brought up about adding more income bins or disaggregating the data in a different way. And, I think in order to do that, we'll need to do some careful thinking about assessing the representativeness of the underlying survey data if we were to go with the SOI data, or the CPS data. We have this implicit assumption on fringe benefits that could be modified with some more information, and we have some ideas about how to do that with some information from BLS. And we haven't really talked about in-kind benefits. We're trying to figure out how that's incorporated in some of the input-output tables, if we can parse that. And then finally, we've made a lot of great progress on this work, and sort of one of the next steps that I'm keen on working on is comparing the household data with something like IMPLAN to sort of facilitate some sort of comparison. So that's basically it on the calibration routine. Tom, do you want to chat about some of the modeling applications? I can drive the slides. You might be on mute.
Oh, Tom. Oh, he's muted.
Oh, my problem.
No, sorry, Tom. I wanted to unmute you. Now I muted you. Sorry, you're muted again. Okay, Tom, you drive it. Okay, sorry for that.
No worries. So, the proof of the pudding is in the eating. So it's also the idea here when you do a lot of work on data, I think it's a common sort of error, the amount of effort involved in sort of organizing the data set is like, at that point, you don't want to actually do much diagnostics because you don't want to find that you've made mistakes and stuff. But our objective here is to try to both diagnose what's interesting from the data that we've been able to reconcile and identify problems we might have. And also, I think there's a general sort of interest in generating a larger set of sample applications in the core set. So that's our objective here, is to move toward that. And this is sort of a first step. What we're doing here is just working on a model that has dynastic households as one of the key things we're doing here in this data reconciliation is accounting for sort of steady state growth path and reconciling investment and capital stocks. That consistency between what's the magnitude of the investment expenditure and what's the earnings on capital hinges on sort of Tobin's Q, and it's something that can be ignored in a static data set. So input-output tables don't have that consistency built in, and so one of the important things, and anybody who builds a dynamic model, you have to do that reconciliation, and rather than leave that to the modeler, we thought we'd build in a version so you can pull off a version that's either calibrated verbatim to the input-output table or one that has a reconciliation of investment and savings. And then what's interesting, once you get that dynamic model set up, you're interested in, like, does it matter, right? So we have 3 different models we look at. One's a static model where the capital stock is intersectionally mobile, but aggregate so it's a comparative static framework. Another is a steady state model, which basically hinges on this idea that Tobin's Q is calibrated to be 1 in the benchmark, and then you do a counterfactual for the aggregate capital stock adjusts. The welfare results that come out of a steady state analysis are can be problematic because they don't account for the investment response required to reach the steady state. And so we also then build a transition intertemporal model in which households are dynastic. So in our advisory board meeting was some interest, and we have methods for handling OLG versions of this model we'd like to develop this year as well. And so then we have an application where we look at the marginal cost of funds. In other words, at the margin, was the cost to raise revenue for each of the sources. We look at energy taxes, where we use the base data set and compare that with Blue Note to see what we get from that. And then we do a final experiment where we bring in occupational data set, and we put some shocks to what the employment costs are that mimics what's going on with COVID, and then we can look at distributional effects across households. I'm not going to show you any results. I think I'm just going to conclude at this side and say that our objective is to write 2 papers based on this work. One that goes through the details of how the household data was constructed, and then the second would be, okay, we have the household data. What are things you can do with that? And so this is a beginning list of what we're looking at doing in that second paper. And we have operational models, and when the WiNDC version 3 will be posted in the next couple of weeks. We've already released a pre-release to the board members, and we're working on a final version we have sort of operational. We'll include these models that go through this as a starting point. So this is sort of work in progress. I don't want to have David wait too long, so I guess at that point maybe should we take questions for 5 minutes, and then David, I'll take the time that we've gone over. I'll take out of my talk. So you've got the floor, but maybe first, if there are any questions of Drew, we're open.
I'm also happy to share the slides. So if anyone wants to take a look at it later.
Okay, well, if there's not anything immediately, you'll be able a chance to follow up on this and look at all the details. One of the things, again, this work has followed the one thing I just add is that our objective here is not to simply produce a data set, but also to produce sort of open source code that shows how that data set was developed. So you'll not only can you see what comes out of our approach, but also what the steps, specifically what the steps are. The GAMS code will all be posted on the website as well. I'd say that the one thing that emphasis I sort of may have had undue influence. I hope I haven't led Andrew astray on this, but the decision to lean on income elasticities rather than household expenditure survey for calibrating preferences comes from, over my career, I've done CG analyses with multiple different household types, maybe I had a half dozen or more papers, and I have yet to find an application where income didn't drive the welfare results. So we're sort of reflecting that. We decided to put our emphasis on the income dimension rather than the expenditure dimension, because in my experience, you can take a heterogeneous household, and you can impose common expenditure shares on all the households without changing the data set and do the same simulations. And I've yet to find a result where that becomes the crucial effect, even though in the policy dialogue, expenditure shares play an important role. And there are certain settings where, like, low income expenditure for energy is higher, so there is an effect, but overall the effects through income we found tend to be dominant. And so at least at this stage, we haven't performed that. Now maybe some student will come along and want to test on my assertion, but that's where we stand.
Yeah, just a quick question. Sorry, this is Madan. I think this is very useful because there is now increasingly demand for analysis at the household level in the context of climate policy analysis, for example. So, there are GTAP-based models available. So, in those models, typically you have a representative household for the whole country. So if this data is made available, well, more researcher will be interested to do household level analysis.
Yeah. Great. So I'm going to shift over to my Thank you, Manon. I agree with you completely. I think it's not just in energy and environment, but also in lots of settings. Distributional issues are really front and center these days. So David Anthoff is, I've known David for several years. He's really a wonderful, entertaining speaker. He has a bunch of stuff I'll just point to. If you want to learn more about this stuff, his talks on YouTube about Julia are really great. So I'm really happy that he agreed to come and talk for us a little bit. So I'll let you take over. It's now about 10 after, so you have about, I say 30, 35 minutes. So I'll leave 15 minutes at the end.
Okay. Thanks, Tom, for inviting me. Hi, everyone. Good to meet you all. So it's a pleasure to talk about this. The thing that I do want to present today is an attempt to bring MPSGE onto Julia. So that's the topic here. I should say that I myself am not known as a CGE modeler, and I don't think I am. I could call myself that by any stretch. My academic work really has been on other things in the past, but I've always followed this field, and I'm very I'm doing a lot of work in sort of computational and software development in that space. And then Eli Lazarus, who's also on the call, who's a PhD student in my department, a couple years ago started to really get interested in CGE modeling, and sort of the combination of me being interested in the technical side and having enough training in econ, which is my home discipline, to, you know, and having been around CGE modelers but never having done it myself, and Eli's interest really in CGE models spurred this this development. So
David, David, excuse me if I interrupt you. We can't really see your screen. Can you share it differently?
So can you, if you just, that will be tricky. Can you just, if you can make me like large, does that work?
Oh.
Hi there, Angel here. If you select stack rather than grid, you can make it work.
So you just, so I will not use WebEx screen sharing feature. I will just, my video feed will have my slides on it.
Yes,
so
but it's so small we can't see your slides. I understand what you want to do, but we can't see anything on your slides.
You can click on the dots on David. Each individual can, and you can basically spotlight him. I don't remember what the word is in WebEx. Yes. And that'll make it so that you can see him much larger.
If you select in the layout, select stack under stage, and it will work perfectly.
Ah, right. So under layout stack. Okay.
Correct.
All right. Okay, good. Thank you. Sorry for this.
Yes, great. Thank you.
Okay. All right. So this is sort of the roadmap, what I want to talk about. Sort of a quick summary of what we want to do there. Then I'm going to talk a little bit about Julia. I'm going to try to demo the whole thing, that what we have at this point. And then I will go a little bit under the hood, and then where we are heading, and then sort of conclude. I'll try to go through this relatively quickly, that we have a little bit of time at the end, because I kind of feel we're such newcomers to this community that it, you know, at least Eli and I would benefit most from feedback and thoughts and so on. So what's the goal with all of this here? So I think sort of the long-term vision is that we would like to create an open source version of MPSGE that is runs on the Julia language, which is a computer language. So that's sort of the, you know, if you ask me where do you want to be in 5 years or something like that. Where we are at the moment is that we have a very rudimentary prototype that can do a couple of things, but it is by no means ready to be used for anything serious. But I think it's sort of, so here's what where I think we are. I think it's complete enough, the prototype, that at least I am convinced that we have sorted out most of the technical sort of software-y design issues that one might expect in this kind of situation. And now there's a lot of work left to actually make it feature complete. But I think the underlying software architecture is pretty solid. So that's sort of the high level idea here. I should say I think about this really as complementary to everything that everyone else here is doing. You know, hopefully this will just be another way to get MPSGE into as many hands as possible. That's sort of the goal here. I am going to show you a link where you can run some of this stuff yourself, but I just want to put out a warning because we're so early in this whole project. We literally, I think, started in February. We are breaking things all the time and we're changing the design. And so it would be fantastic if people want to play around with this and give us feedback and get involved, but don't build something that really requires stability at this point. Okay, so who are we? So Eli is a PhD student in the Energy and Resources group, and myself, we're like really the team that has been working on this since February. Then we've had a lot of interaction, or a fair bit of interaction with Tom, and then the group at NREL, Max, John, and Caroline, and all of them have been really helpful, with guidance and advice and feedback. And we also kind of need that because both Eli and myself are newcomers to this community. So having interactions and feedback from people that have been around longer is, I think, really crucial for this project to stand a chance to succeed. All right. So I think what I want to do next is I want to talk a little bit about Julia. This is the programming language on which this whole effort is based right now, and then I'll talk about the MPSGE story specifically. So what is Julia? So Julia is a new programming language that these four folks, Jeff, Stefan, Viral, and Alan, created they released the first version in 2012. Why would anyone be interested in using yet another programming language? Well, this is the blog post that they used to announce the programming language to the public. And for us as economists, you have this little tidbit. They started the introduction with "in short" because we're greedy. So, of course, the economist's heart was shining at that point. This is the spirit that we like. But in all seriousness, they were greedy in ways that I think are really helpful for projects like MPSGE and modeling and so on. So what is it? So it was created at MIT in the applied math department. So all the four folks that started this project, so Alan is a professor in the applied math department, and then the rest of the team were younger folks that were in the applied math department at that point. And it's a language, a computer language that is specifically designed for scientific computing. So it's Python is used widely these days for scientific computing, but it was never built for scientific computing. It's a general purpose programming language. And then it happened that a bunch of folks created some really good packages that make it useful for scientific computing, but the language itself was never purposefully designed for that. So in that sense, it is maybe more like Fortran, right? It was sort of purposefully built for scientific computing. It's completely open source, so it's MIT licensed, so you don't pay for it. You can modify it. You can contribute very easily to it. There are thousands of people that have contributed to the language at this point. So that's great. In general, it's a simple language. So it's as simple as Python and R. So you don't have to. So if you're familiar with R or Python or MATLAB for that matter, and you look at Julia code, you will immediately feel at home. There's really they wisely made the choice to not be clever, but reuse a lot of simple syntax ideas that people are familiar with. But it is as fast as C or Fortran. So that's sort of like the key selling point for the language. You can write code that looks as simple as Python and R and so on, but your loops are essentially as fast as a C or Fortran routine. And the reason for that is that under the hood, the language actually uses the same compiler backend that is used in a lot of C compilers these days. So it's really fast. And you can do really low-level work if you want to. You don't have to, and most people don't, but it has that capability. And then I don't know how many sort of programming geeks we have here on the call, but it also it is a really powerful programming language. So those of you who are familiar with Lisp, it has actually a lot of inspiration from Lisp. And that makes it a really powerful tool for meta programming and those kinds of things, which is very, very helpful when you start to think about building something like an MPSGE-like environment. The timeline for this was that it was originally, the first public version was released in 2012. In 2018, they released version 1.0. There was a conference in London that I still remember. I was there when they actually hit the button to push out 1.0 into the wild. And since that 1.0 release, the language has been very, very stable. And it has been picked up by so many groups. You know, the Federal Reserve in New York is using it for their main model. Lots of labs, national labs are using it for their models. It's, you know, I would say from 2012 to 2018, there was always the question, will we be able to establish this? I think that the language at this point is well beyond that point. Okay, so yeah, so the language, as I said, is general purpose scientific computing. That's sort of the target of the language. So it's really excellent at everything math. So, you know, there are lots of mathematicians that work and contribute to that. So anything linear algebra, special function. I mean, there's almost no area of math that is not really powerfully and well represented on the platform. So that's just all covered. It has all the data manipulation type packages that you might know from R and Python. So if you work with tabular data, you need to reshape it, filter it, and so on. All of that is there. There are an amazing set of plotting libraries that are all state of the art. It has really good distributed computing facilities. So if you want to run things on a cluster, it's all sort of built in into the language. It's also fully integrated into sort of a modern scientific software stack. So some of you might be familiar with Jupyter notebooks, for example. The name Jupyter, the JU, the first two letters, actually stand for Julia. And so Julia is the first class language in that whole ecosystem. There is excellent, so now there will be a disclosure in a second, but it has an excellent integration into the VS Code editor. Take this with a grain of salt because I built and maintained that part, so I'm clapping myself here. That's sort of maybe a bit embarrassing. It's tightly integrated into GitHub, into the binder infrastructure, and at this point, I've kind of lost track about all the integrations because there's so many groups that work on making sure that Julia is sort of a first-class citizens in what I would sort of describe a modern software stack these days. And then sort of a little bit closer to, I think, the topic of this group here. One of the application areas where Julia has shined from the get-go is numerical optimization. So there has been, I don't know whether this is a coincidence, but you know, sometimes these things happen. Some of the people that got involved with the language very, very early on were people from OR that were working on optimization in the optimization space. And so there is an enormous amount of solvers that are either integrated, you know, existing solvers that are integrated into Julia. There's a lot of research being done that people write new solvers in Julia. There's an enormous infrastructure around packages that help you run optimization. So that, for example, I think the automatic differentiation ecosystem that exists in Julia is really unparalleled anywhere. And one really fantastic thing is that a lot of the groups that work on the OR aspects of this, sort of that research the underlying methods, there are a lot of groups that are using Julia to actually do that research. So it's very much cutting edge, not sort of re-implementing and catching up in that particular space. So that's sort of great news. And then I mentioned that this sort of that Julia has all these Lispy type features. What that means concretely is that it's actually an excellent platform to create what's called domain-specific languages in computer science lingo. So you have sort of the syntax of Julia itself, but then Julia provides a very easy way to create subsyntax things for specific domains. So you can, for example, create your own syntax for optimization that is completely embedded and part of the normal Julia syntax that you add to the language. So that's sort of maybe a high level description here. But that is sort of excellent for, so for example, in the optimization space, there's a huge amount of packages that essentially create something like GAMS, like specialized syntax for formulating an optimization problem. But they're completely embedded in Julia. So they're little sub-languages within the Julia language. And the Julia language from the get-go was designed to support that kind of structure. So that makes it a really good platform for those kinds of things. All right, so I should maybe I think most of you probably don't know who I am, but those of you who know who I am, probably know me mostly from my work in climate economics. That's sort of where I think I made my name in the academic field. But I've actually been really active in this Julia community. So I think I joined the whole sort of effort around version 0.2. At this point, all my research on climate economics, social cost of carbon is all based on Julia. I've built various major sort of efforts on Julia, but one is this MIMI platform for computing the social cost of carbon. But then outside of my economics and research work, I've also contributed just to the Julia ecosystem in general. So I created and maintained the Julia language extension for VS Code, which at this point is the main integrated editing environment for Julia people. So I think we have like 200,000 users at this point. I created a whole ecosystem of packages for data manipulation called Queryverse. I created a plotting package called VegaLite, and then sort of a lot of random stuff. So I think I'm really steeped in the Julia ecosystem, and from my point, that's actually what I probably bring to this MPSGE project. I'm not a CGE modeler, so that's sort of not my area of expertise, but I know Julia in and out. So I think in terms of sort of technical, how you would pull something like that off on the Julia side of things, that's I think what I really can contribute to this project. Okay, so that was Julia. So this will be a bit interesting whether we can pull this off. I want to just demo Julia to you. No, the package that we created for MPSGE actually, and you can actually you can run it yourself if you want. So here's a link that you can see on the slide. If you put that into your browser, it will spin up a virtual machine in the cloud. It will have everything installed that you need to run the example, and then you can run it. It opens up a Jupyter notebook with a very simple example of solving an MPSGE problem in Julia. So if you want, you can try that now. And I'm going to show you the same thing here on my screen. So let me just go over to my Jupyter notebook. So here I'm in Jupyter Lab. This is a Jupyter notebook, and the same thing is hosted for you on that link that I showed you. And I'm just going to run through a very simple example of where we are at this moment with our prototype. So here I'm loading the MPSGE package that we've published into the registry. Then you create a new model with this syntax here. So we're storing that in a global variable m, and it's a new MPSGE model that we've created at this point here. You can create as many as you want and sort of all have them hang around. And then now we're starting to interactively add stuff to our MPSGE model. So the first line here is that we add a parameter to m. The name of the parameter is endow, and the value that we give it is 1. Then we add 3 sectors to our model m. So each of these lines here adds 1 sector, x, y, and u. Then we add 5 commodities to the model. And those of you who are familiar with the 2x2 example from the MPSGE documentation, you will have some recognition here. All right, then we add a consumer here, RA. We give it a benchmark value. We add 3 production functions here. So we specify various things here, the elasticity, the benchmark value, and then the inputs with their benchmark values. And then here at the end, we specify a demand to the model. And note that here in the endowment, we are referencing the parameter that I had created originally. So this is sort of where we can use parameters that we created in arbitrary expressions, like this one here, where we set the endowment to 70 times the parameter value. All right, so at this point, we've built up an MPSGE model M that is the 2x2 example. One thing that you can do now is you can look at an algebraic version of this. So this will just analyze your model and then spit out the equations. And it's a bit silly, but I spent so much time trying to make sure that we get this symbol right here so that you can see what the complementarity conditions are. Yeah, so but that is sort of an easy way to specify your MPSGE model and then automatically get the set of equations, the algebraic formulation of your model. We've used this a lot when we built this to check things, but I think this is sort of generally useful. All right, and then we have our model M and we can solve it, right? And the first thing we probably want to do is, I think what Tom alluded to, is check whether everything is correct. So we solve the model, we say the cumulative iteration limit is 0, and that means we actually don't want to solve it, we just want to check it. I think that's sort of the same method that you typically use in the GAMS version of MPSGE. And all right, you can see we're using the path solver under the hood. So this is all linked up with path, and it solved it. And then here, just one more example. I can set the value of the endowment to 1.1, and then I can solve again. And then here we have our new solution. So, so this is essentially where we are in terms of code. So it runs, it works. Be warned, if you deviate much from this example, it will probably no longer work, but we do have something that works from the beginning to end. All right, so next, what did I want to show you next? Yeah, I wanted to briefly dive a little bit into how we built this. What's the design here? What's the architecture that we've used for this? So at the bottom of all of this, we're using the path solver. So this is a C library that you all know. I think it's the same solver that is used in the GAMS version of MPSGE. We're reusing the same thing here because that's a major piece of software, and we can't replicate that easily. So we're using that. There's a Julia package called Path Solver that wraps the C library path. So a different group produced that, so that makes it very easy for us to reuse that piece. I should say my color coding here is that gray means this is a part that is written not in Julia. So path is written, I think, in, I don't even know, is it C or Fortran? But everything in blue is Julia packages. So path solver is a Julia package. So that's one leg that we stand on. Then the other leg is that we stand on the automatic differentiation ecosystem that exists in Julia. So for the function evaluation, we're not writing our own function evaluation. We're reusing what exists in Julia. And there's a vast ecosystem of autodiff packages that help us create really efficient evaluators for the objective, for the constraints, for the Jacobian, and all of those kinds of things. So we're standing on that. And we're interfacing with that autodiff interface ecosystem via the jump package. And so jump is the package in Julia that is the primary optimization package. So if jump is really the equivalent of GAMS in Julia. And so jump gives you the ability to specify variables, specify constraints, specify an objective function, and then interface with lots and lots of different numerical solvers. And so that lives all in jump. Now, what jump does not have at the moment is support for nonlinear mixed complementarity problems, which we, of course, need for our system. So if jump had support for that, we would actually directly use jump for everything, but it doesn't. So we're then using another package called complementarity that is built by another group, which adds on top of jump support for nonlinear mixed complementarity problems. And this is also the package that interfaces with the whole path. stack. So essentially, mixed complementarity, that package uses jump for function evaluation and automatic differentiation. It uses path solver for interfacing with the numerical solver under the hood. And it provides an easy way for users or packages like ours to solve mixed complementarity problems. So that's all of those packages are the ones that we stand on top of. And then MPSGE is the package that Eli and I created over the last couple of months. That's actually the package where we contribute something. All right, so now let's dive into that package a little bit more. So really at the heart of that package is the following step. We have a whole bunch of data structures that hold the structure of an MPSGE model. So this is, a list of sectors, a list of prices, a list of production functions, and a list of demand functions. That's essentially, I think, it. And so those are data structures. And then we have a step that translates or generates out of those data structures the algebraic MCP formulation for that problem. And then we hand off that algebraic formulation of the problem to the complementarity package and let it handle everything else. So this translation step from the MPSGE data structures into an algebraic formulation is really the heart and soul of the package that we've created so far. I've had a really interesting and long chat with Tom a couple of weeks ago about MPSGE 2.0, this Ruby thing that I think he will talk about after I'm done. And I think that's actually, I think that design is actually very similar, because my understanding is that is also taking essentially MPSGE data structures and then translating it into an algebraic version and then handing that algebraic version off to an underlying system that does all the function evaluation and so on. So that's sort of really where we're spending most of the time right now. And then on top of that, we currently have one API. That's the one that I showed you, the thing that the actual user of a package like this will see and interface with. So the demo that I showed you is what I call the jump-inspired API. It looks in many ways like other Julia optimization packages look like, and that was the goal. Okay, so that's one API here. There's really no reason that we can't add other ones in addition to that. This is sort of just the surface API layer. It's not super involved. So I think Alex Martin came up with that idea at some point. It would, I think, be eminently feasible, for example, to add another, thin surface layer API that accepts original MPSGE syntax directly, and then also interfaces with that. So in my mind, getting these surface level APIs right is really important, and it requires a lot of design iteration, but that's not where the bulk of the programming and complexity is. That's really in this step down here. So we're iterating on this and we're fine tuning it, but I think sort of adding another one or something like that later on is not a gigantic task. So that's sort of a little bit of how this works under the hood. So roadmap, where is all of this going? So to be blunt, at the moment, the biggest problem is that Eli and I are sort of fascinated with this idea. We kind of stumbled a little bit into this and just started and ran with it. And I think we got pretty far, but at the moment, we don't have any funding for any of this. So I think that's sort of the biggest roadblock at the moment. Both of us would be keen to make this like a major part and really take this serious, but I think that's sort of something we need to figure out. And in terms of the things that actually need to be done, going from this prototype to something that actually can solve more interesting models, just to say there are a lot of things that are missing that we're aware of. And then I'm actually sure there are other things that we're not aware of that are also missing that anyone who's been around in this community longer than the two of us would immediately pick up on. So I just really want to stress that we've built sort of a simple prototype to demonstrate the technical design, but we're far from having something that is complete enough to be used for anything real, quite frankly. But so here are some of the things that we know we're missing right now. So certainly set notation, right? So right now it's essentially like a scalar version So I think this is one of the big ones that we need to fix. Really, at the moment, if you try anything more complex than the 2x2 example, things will probably break. We don't have anything like support for taxes or anything like that. A lot of the elasticities that you can specify at the moment are actually ignored when we translate things into the algebraic formulation. We just assume it's 1. So there's a lot of detail like that where there's no technical difficulty there in sort of from a software design question. It's just, it needs a lot more time to get the details right. And then I think at some point we really want to make sure that we integrate with a data pipeline. I should say, I think both Eli and I feel that is definitely outside of the scope of what we could do. But I don't even know how we found it. Oh no, I do know how we bumped into the NREL crew. Because I think Carolyn gave a talk at the Julia conference about their work. So we've been talking with them, and they've been building a Julia data pipeline that I think builds off the WiNDC work. So I think our plan there would be to really integrate tightly with that, so that at the end, fingers crossed, we would have sort of all the data availability from the work that the NREL group is doing, and then we would provide sort of the modeling exercise, the modeling platform. Okay, so I'll try to wrap up. So I'm at a point. So in February, when Eli and I started this, I was like, let's play around a little bit with this and give it a go. And Tom and I had talked about this a couple of times, and so I said, why don't we give it a shot? But I was not at all confident that we would actually be able to pull this off. I'm now confident that this can be done. I think we're far enough, and we've gone through sort of a couple of iterations that I think with enough resources, we have the expertise and the path to sort of finish this. I think this has really great potential to bring the whole MPSGE story to a much larger audience than it is right now. I mean, just first of all, because it's free. But I also think there are a lot of people these days that do computational work that, especially in sort of the student, PhD students and so on, and they don't start with GAMs. They start with these open source scientific computing ecosystems. And I think if MPSGE was available on those platforms with a very low barrier of entry, I think that would open things up greatly. Also, just things like for teaching. I don't know if you can run everything in the cloud in a web browser, that's just really helpful. And then I think another real benefit is, I think GAMS is fantastic. I really have to say, from a computer science point of view, the foresight that you can see in that system is just amazing. But on the other hand, it is a little bit of a silo in itself, and so many tools are being developed in other more mainstream languages that it's a little bit difficult to use from GAMS. And so I think if MPSGE was available on a more mainstream language like Julia, it would make it so much easier. If you want to combine modeling with really intensive data manipulation work, or fancy visualizations, or running things in a distributed fashion on a cluster, or embed an MPSGE model in some larger algorithm, all those kinds of things I think can be really efficiently done if you have the MPSGE part as part of a programming language like Julia. So I think that would just open up new opportunities there. And then I'm not sure about this actually, but maybe this would make it easier for newcomers to actually contribute to MPSGE itself. Who knows? My gut feeling right now is that the technical skill required to, for example, contribute to the package that Eli and I have created, I think the technical skill required to do that is probably lower than to contribute to Tom's Fortran MPSGE sort of code base. I'm not sure, maybe I'm wrong. But I think I could see a world where maybe if this is an open source project on Julia itself, where people can contribute to MPSGE itself directly, maybe it could actually attract more people to help out with that, which would be great. I might be completely off on that one, quite frankly. So who knows? All right, and that's all I had. Here are various links. This link here is the link to the package as it is right now, and then this link down here is a link to a GitHub repository with the replication code, or not replication code, for the demo code that I showed here. All right, and then I think that's all I had. Maybe happy to answer any questions.
Really wonderful, Dave. Fantastic. So we're open to questions from other folks. If anyone else has anything to offer, I'm ultra impressed. I think this is ultra cool. What will turn the key will be that my guess is that Julia will become a very effective tool for doing data work and manipulation, because it has, for exactly the reasons you've pointed out, it's free. Students get up the learning curve. This will run, and as soon as it's there, then having MPSGE there would really be a very useful thing. So I think it's really great. My only impression of reflecting on your work with Eli, it's like, reminds me a bit of when the web was first developing around the year 2000. I got a grad student and I had this idea of this new scripting language that came out called Perl, where you could build web interfaces, and we built a web interface for running models, doing the model policy analysis in the web. There was one earlier prototype of this, and he wrote a paper about that for the Perl journal. And then I lost the student because he got an offer for 6 figures he was like scheduling softball leagues or something, writing software. The funny thing was he came back and finished his PhD, but he funded it himself. He made enough money.
So Eli, there you have the right strategy, but please don't leave me for a yeah.
He's been very successful. The student was great. He's done all sorts of stuff, and it's cool. So I think the idea of getting on early and getting up the learning curve before the rest of the world does, it takes a little bit. You have to be a little bit brave, but I think it's great. I love it. So I'm very enthusiastic about this project. I think it's great. I think that my own take on it is the step of going from scalar to indexed code may be harder than you realize, but we'll see how this works, right?
Yeah. So when we last chatted, I think that my takeaway was that's the thing we need to tackle next.
This indexed modeling. I mean, you have all the stuff. You have this, what are they called? It's called associative arrays you already have in the language. You just have to learn how to use those in a way that you can talk to the MPSGE code.
So one thing on that in particular is that the way we want to do this right now is that we will not undo the set version of the model. We would hand off a set version of the model to complementarity. So our plan right now is not that our MPSGE level essentially unrolls all these sets, but instead that we actually pass a set version, a set algebraic version to the complementarity package. And my hope would be that sort of reduces the complexity on our end, but who knows?
The problem is always that having a set version. I mean, there's this flat set version where you have a matrix A is m by n, and you just have scalar index running. It's any index you want is fine as long as it's numeric. It's the standard sort of mathematician's approach to sets. Whereas to handle policy applications where you're trying to package complexity through using symbols so it's easier to interpret what comes out of the model, then you want to have exceptions, and the exceptions are always what drive you crazy. The current MPSGE code has perhaps too much flexibility, and you can put a dollar exception on virtually anything in the model and suppress things and add stuff, which is both a strength and a weakness of the language. It's a strength in the sense that we can handle arbitrary complexity. It's a weakness in the sense you get models that are ultra complex, right? So there's always this trade-off. But I'm confident that you guys will figure out something that's useful, and you don't have to have a perfect representation of the MPSGE code to make that useful. So I think it's great. So we're down to the last 10 minutes. So I agreed to do one last talk, and so I'm just going to sort of look on no hands. I'll show sort of MPSGE version 2. This Julia, it's a code that basically uses Ruby to do the translation. I'm going to rip through the slides really fast because I just want to show you what I'm going to conclude with, to show you a cool something. We can do something with this that we can't do with MPSGE. So that's what's cool about it. It's like And I'll in fact not just show you one, but two. So my main objective is just to give enough motivation for this. I need to give credit to Jim Markison, who's always been pushing me on doing, Markison recognizes the way we handle Dixit-Sticklets in the current MPSGE code sort of is stupid, and we need to improve upon that. And Florius Landis, who's basically absolutely a wizard programmer, extremely good, who I just, when he joined my chair at ETH, I said, oh, Florian, why don't you have a look at Ruby? This looks like the cleanest code around for doing a lot of this stuff. And he basically picked it up and basically went off to do cool stuff with it. So he's a really smart guy. He was at CW Mannheim. Now I think he's associated with ETH again. So MPSGE, I won't tell you about this. This is the basic sort of motivation, is to do something that captures the complexity of the underlying nonlinear functions. It was motivated by, early on, this was motivated by Orchard Hayes. So I was studying operations research, and I just thought that Orchard Hayes' stuff was ultra cool. So MPSGE was this idea of doing that, but it's immediately jumped to this much more complicated model that where we have indexing and we have exceptions and we have, so this is what the way the GTAP model looks like. What's cool about it is GTAP, you write down the GTAP model in GAMS algebra, you're at sort of 8 pages. If you write it down using GEMPAC, you're at 20 pages. So it's, whereas you're doing MPSGE, it's like all in one page. So the virtue of this is that it really is very compact representation. It has this interpretation that it's almost like a variational model. And so variational inequalities are very compact in notation, and that's really what it's doing. But the current version is kind of crazy because it basically unpacks the whole model. And so when you run MPSGE under GAMS, it writes GAMS code to dump the data out. And then the data gets generated onto a big, long text file. And then I read the text file. My Fortran code reads the text file. And then it has this GE MPSA, which is this evaluation of all the functions, which is all handling the thing using Fortran 77. And I was kind of chuckling at your reference to the user community for MPSGE. This code was written in this. I did a first version in 1982. I did a revision in 1990. At the time, I was in the middle of one-year contracts in the econ department of Western Ontario, and Markison and Harrison told me, just write economics, stop writing Fortran. And so I basically did one pass at this, got it over to the guys at GAMS. And to be honest, David, I've not really touched this code since 1990. It's the same code. I got it working right, and then I basically didn't mess with it. And the guys, Steve Dirks at GAMS has basically updated certain things, memory allocation, but basically it's the same code. It's not been touched. The beauty of having it in Fortran is that you can scope variables so that you can do things like checking for whether or not the model is consistent. And that's more than just, does it satisfy the benchmark? When something is logically wrong with the model, the beauty of MPSGE, what gives us the leverage is that it comes back and says, wait a minute, you have a consumer here who has income, but he doesn't demand anything, or you have this good gets produced, but it doesn't get used anywhere in the economy. So this checking of the logic of the model is really where the strength comes in. That's sort of how WiNDC moves fast in terms of matrix balancing, is we lean on MPSGE to tell us stuff that doesn't make sense. So format is this basic. Matheson wrote this paper in 1986 that basically gives us this leverage. And the key thing is we have this, the central model is basically Arrow-Debreu in a very compact format. It's a dual version of Arrow-Debreu. And then we have the get out of jail free card is the auxiliary variables. And so that gives you the basic logic. And so you can write this thing down tight. But the key thing is you have this flexibility to write these side constraints, these F variables. That's where you really get the leverage of this, is you can write that stuff in GAMS. So we like to keep GAMS, but the beauty of the Euler jump format is you can do the same thing. You can basically extend this to have, you can write some jump equations to go along and throw those in to handle some stuff that's, so these auxiliary variables are really where the logic, this was motivated at the time I developed MPSGE was to develop, I just wanted to be able to do test problems more easily for my algorithm. I was trying to solve nonlinear complementarity problems, but I was annoyed by how much programming was required to generate these models. And I discovered that I came up with a model representation that made it very easy. I could take someone's model out of an economics paper and write it down in an afternoon and be able to do all and verify I could solve the model. So that was really what my motivation was. So data learn a lifetime to master. You have to understand CS functions inside and out. You have to understand nesting. There's this issue about how to handle margins, multiple taxes in a single transaction, absence of algebraic GAMS code. These are all things that, in terms of what are the barriers to MPSG, is that someone who's getting started doesn't understand what it's doing, doesn't have an easy introduction. So that's again, your approach of give me your MPSG model. Here's what the algebra is. I'll show it to you nice and clean. This is a winning solution for making MPSG available, to have it be transparent. So MPSG version 2 was this idea of writing self-documenting GAMS MCP code. I'm not sure we've accomplished that. We do. I'll show you examples that generates the code. The problem is that because GAMS has a global scoping of variables, all the variables and all the parameters are global names. It's tough because the number of symbols you need. If you unwind the MPSG, then you have lots of symbols for shares of this. You have not only just shares for every input in every sector, you have to know shares of this input in that nest and shares of that nest and this other nest. So there's lots of names that you need, and that becomes a problem. So I'm not sure what we're generating. I'm not sure whether it'll ever be ready for prime time, but I'll show you what's cool you can do with the existing code. We also introduced this external effects, so an additional version way of using auxiliary variables to address Markuson's concern with how we can represent Dixit-Stiglitz variety effects. And then it also provides, so there's a variety of things we'd like to do here. So this is what the code looks like that gets generated. So we generate equations, but there are lots of conditional conditions that go in, and there's lots of these names are sort of ugly, but that's what happens when you're going to show me the algebra. Okay, I showed the algebra, but you're not going to understand the algebra. The MPSG code starts to look relatively more appealing after you've seen the algebra. So that's the basic logic. This external effects model is this idea that we have this multiplier mu. You can take an auxiliary variable and put it in as a productivity effect on an input, and that gives you the ability to handle externalities. So you can have the coal plant next to the laundry and show that effect, but you can also have this effect where you get variety effects, so that you get this you can get a variety effect operating on this thing that gives you productivity impacts, and that's essential for doing any sort of these new new trade theory models. So that's the basic sort of logic. You get the Jevons paradox. You get a variety of effects there that's nice. So this is what the Ruby parser looks like. It's kind of embarrassing because I should have written this paper up 2 years ago. And again, it's the sort of thing that I have the system that works. I'm too busy using MPSG to write up version MPSG 2, but I feel motivated to do that. And I particularly in preparing for this talk, I'm particularly encouraged. I go back to look at it. It's like, man, this is really like my co-author's work. Florian's work is fantastic. You know, this Ruby parser, the MPSG parser is 80K, and it's got 60K of classes, and then there's this MPSG. The core thing is really tight, and this generates this writes out the whole algebra. It relies very much on all these algorithms comes down. These new codes rely on knowing how to handle regular expressions, so it has all sorts of fancy stuff for doing the parsing. So I'm going to shift over to show you. So here's the external effects model, but I don't have time to go through it. But basically, you have the endogenous markup, and you have this XV that shows the variety effects. So that this is a nice way to do Dixit-Stiglitz variety effects. That's one of Markuson's models that has markups and so forth. But let me just go over the cool thing you can do with this is, so here is GTAP 10. There's an MPSG version of the model. The cool thing about it is it's indexed, right? So this is off the shelf. It's an MPSG model. It's got indices, and it's using the GTAP and GAMS notation. There's a couple things that were simplified. We can't handle complex nesting and lots of exceptions we can't handle so well, but the basic the core model we can handle. And then, so there's the MPSG model. Rather than calling MPSG set, that's calling my Fortran code, and here we have this include library MPSG.gms that basically is a wrapper around the Ruby model. And then we have the same thing where it generates GTAP 10_gen. It's a generator code that, so we still need some code before we solve the model, but that's GAMS code for assigning. What that thing does is, if I look at, so what's the gen code does, it assigns at the point where you say solve the model, I need to write the GAMS code that assigns all the value shares. So this is keeping track of at the point that you solve a model, what are the value shares, what's Q bar, what's the condition. So there's a whole bunch of conditionals that we have to assign. We have to assign taxes. So this is all the data that goes into the algebraic model gets assigned. And we also assign some bounds and so forth. We assign what the values are. So that's basically just all the stuff that MPSGE would otherwise be doing, that's doing. So that's all cool, and that's solved. So the iteration limit 0, we get a hand check. We can read in what the tariff database is, so we can do a calculation. So at that point, again, that's the same thing. We can do a calculation at that point. But here's the cool thing about the assisting code. This is the thing that, why do I want to have MPSGE version 2? Is I want to declare a model where I choose which region I want to maximize, whose consumption I want to maximize. So I declare a set R max that says what region do I want to maximize. And then I want to take my MPSGE code and throw it into a nonlinear program. So that says, now it can be an MPEG or it can be a system of nonlinear equations. We're going to solve this using Ferris's MPEG tools. So that says, take the complementarity problem, put that as constraints, and then I put in the objective. And then I can solve optimal tariffs. So I can basically put a little bit of procedural code in here. I do a loop, a Nash loop to do solve one region and then the other region, and I can compute the Nash equilibrium tariff responses in the GAMS model. And that's something that nobody, I mean, up till now, if you want to do that, you have to write out this stuff algebraically. And here we can leverage the code to generate the Nash iterations. So I do 4 Nash iterations, and then I can basically go off and I can compute that. And I can, if I add, so this guy, I can say, so here I'm going to say, I can put in what the iterations are, 0, 1, 2, 3, 4, and I can remove these guys. So there's here we see the unilateral, that's the optimal response to the unilateral. In this model, it's highly convex. So this is the one-shot deviation where the regions each optimize taking the tariff rates of the other countries as given. And then we iterate and we see we do have some adjustment in this particular database with the ordinary GTAP tariffs. The tariff rates are very close to the one-shot Nash is very close to the Nash equilibrium, but you can show how this responds over time, and you can compare it to what the tariff rates are in the benchmark. So you can see that the Nash optimal response in the GTAP data set is much higher. So what's cool about this is that it's a new piece of code, but it's not what I wanted to do was to do a tool where we could do something where we could do new economics that we can't do before. And I'm very encouraged by the Ruby code. I just think this is cool that we can basically take this and do something that's not been done before. So I'm really encouraged by this, and I think I view this as being complementary rather than a substitute for the work that David's doing. I like the idea that we have a couple different ways and we can sort of interact with each other. So I want to get this written up right now. This will be something in my game plan was to release this with a version of this with GTAP with WiNDC version 3, but there's a lot of, for exactly the reasons, I agree completely, David, with young guys, they're risk averse. They don't want to spend time using a code where there's a barrier to their continued use of this after they graduate. Moving up the learning curve on the open source stuff has a huge return. I understand completely where they're coming from. So I like this a lot. And so I really would like to see Julia succeed. The version 2, the Ruby code is cool. And what I like about it is that even if it has a short life, it can do things that we can't do. This external effects thing and the fact that we can embed the optimization over an MPSGE model over the instrument set, that's a huge advantage. So we have gone over by 2 minutes. I just want to apologize for.
Oh, no, Tom, we do have plenty of time.
Oh, do we? Okay, I thought we were off by 11. That's good. I wasn't paying attention. So we're okay.
Yes, we have plenty of time for questions about MPSGE and questions for WiNDC in general.
Yeah.
So Tom, I just wanted to mention that structural estimation is possible in that framework also, right?
Yeah. So that's where you take and then wherever an elasticity appears in the MPSGE code, rather than putting it in as a parameter, you put the elasticity in as a variable, and then you can say, take this data set, do a structural estimation, solve the model, say, come as close as possible to what we observed. And that's the standard method for estimating these a variety of applications. The work we did on the Mellitz model used this a lot, but this is, I agree completely. That's a very good observation. So we're open to other feedback. I mean, for people, you know, I'm entertained.
I guess I would just make that additional comment that the algebraic versions of these models, anything that's sort of a real world model, they become incomprehensible really quickly, right? You know, so we all say that we want to see the algebra, but you know, my guess is that you can't, even in MPSGE version 2, you can't yet do things like non-separable nests and stuff because the parameter set just explodes, right?
Yeah. Yeah. I mean, yeah. I mean, GAMS has this external functions thing, and I have a prototype where I built a Fortran code to read the external function and actually do MPSGE style stuff where you can basically write an algebraic MCP model, but then use some higher order markup from MPSGE to represent the functions. And that's another way you could go. But eventually you have to remove this explosion of the number of names you need is where the problem comes in. And how do you create names that you don't have collisions with the user code? This is not. Whereas that's the thing that I love about the Julia idea is that it's built to handle little models inside, and it may be that you ending up someplace that doesn't really reproduce MPSGE at all, but it has the functionality of MPSGE without, you know, there's lots of ways this could go, and I really think that the stuff that David showed me before about how this is built, this is beautiful. And the main problem is I'm a bit of an teaching old dogs new tricks is a bit of a challenge. So I don't know if I'm ever going to get up the curve on Julia, but I'm very enthusiastic about learning how to compartmentalize the complexity so that we can more easily, when somebody says, what's the effect of this? You can basically pull the numbers, write down the logic, do the model, answer the question, right? It's all about like, how fast can we go from the question and the data to the answer, right? It's not about, you know, being famous. It's about like, let's do the work. Let's actually have something where we can answer the question. And I can see lots of ways. If you're looking for ways to add complexity, Eli, I can show you lots of stuff. I have lots of ideas about stuff that you can make this more complex, right? This is, among them is that I have a version now of Logit that sits right on top of CES. So basically, any MPSGE model that has local elasticities to substitution, I can write down algebraically a Logit model that has exactly the same benchmark and exactly the same Slutsky matrix at the benchmark, but different global properties. Damn, this is valuable because then when somebody asks you to do a policy simulation where you go like, you explode things and you move far away from the benchmark point, we always say, well, these are the elasticities, but you're making reference to what's happening at the reference point. And having a second set of nonlinear equations with a different functional form, that's a way of immediately checking whether or not your answer is robust. And that would be really cool to be able to do that. But again, the problem is just the explosion of the namespace you need to handle this is enormous. And that's where the problem is, how to handle this. I don't know there's lots of stuff that's unanswered questions about how to proceed on the software engineering to make this work in a way which is operational.
David, I gathered from talking to the NRail gang that the complementarity package in Julia is undergoing some kind of redesign. Is that right? And do we have a sense like when that'll be settled down?
So this was one of the major questions where I was unsure initially, right? Do we actually have the foundation on which to build this or not? The situation there, but I think I figured this out now. So the JUMP, the package, is sort of the main optimization package, and it actually has support for linear mixed complementarity problems built into JUMP. There are plans in JUMP, the main optimization package, to at some point add nonlinear mixed complementarity support to that. But I think that is not a short-term, if a medium-term priority for them. So I don't think that's happening anytime soon. But this complementarity project, this is a package that sits on top of jump by someone else. For a while they had a message saying, oh, now that jump has mixed complementarity support, we're going to shut down. And then I interacted with them a little bit, and they had misunderstood what jump was doing. They thought that jump already sort of covered this. And once they realized that jump doesn't, they actually said, we will continue to maintain this until there's a like full nonlinear mixed complementarity solution in jump. So and the person who's maintaining the complementarity package is incredibly responsive. He's on top of things. So at this point, I'm not worried at all about that, because I think the complementarity package does what it's supposed to do. The person who maintains it said he will maintain it until if jump sort of picks us up at some point, then it will go away. But I'm not worried about that aspect anymore.
I should say, I apologize because my planning was not, I didn't get to Ferris in time that his schedule was not already full. So the developer, the guy who invented Path is here at Wisconsin. So this is all, and he's been following it. He was a little bit risk averse about jumping in because of the, he wasn't sure that the dust had settled at Julia. So he was not sort of willing to jump on to this, but getting him involved was something that is on my agenda, is to try to interest him in being involved in this stuff, because he has a bunch of stuff. He works extensively with GAMS, and he's very good at this intermediate stuff. It's kind of ironic, the reason he couldn't come to this discussion of this, essentially this computer science issue of the languages, he's busy doing energy economics today. He like advises the utility, so he does. So it's kind of funny, we kind of do both things. But my hope is that with this, that we can interest him in getting involved in the development of this interface.
I should say he must have interacted with the Julia folks and have helped them, because the way this works right now is that if you install this Julia package that interfaces with the Path solver, then that package automatically downloads and installs a version of Path that he hosts specifically for Julia. So I think there has been some interaction between them that is good and led to that situation. I should say one thing. I mean, I think this sort of works, but one thing to keep in mind is that Path is not open source, right? So that is the only piece in this whole stack that we've sort of designed right now where there's a piece of software involved that is not open source. It seems to be sort of free at the moment. That's sort of, certainly I didn't pay anything. And I think you get sort of a license for a certain time. But that is one piece in the puzzle that is, that's not MIT licensed, where everything is just on the table. I don't think that's a big problem, but just to flag it.
Yeah, the problem is these codes that were developed prior to open source, all the licensing being aware. Now, when people develop a code, they think immediately about what license they're going to use. My impression with Path was always, if you call Path from the API, then he doesn't try to track you down. But it may be that if you produce a tool that lots of consulting firms can use intensively, then there may be some concern about that. Ferris is a very smart guy, really great to work with. So if we can get him interested in this, that'd be great. So Eli, nice to meet you. Thank you for coming. It's great.
So I think one other comment that I have, I think what's really exciting is I think actually your version 2 design and what we've sort of started on the Julia side of things, to me, look like almost identical except for language choice in terms of sort of the underlying philosophy, right? So you don't have your own function evaluator anymore, but you actually produce an algebraic version. And maybe it's not for human eye consumption because it's so messy, but it is an algebraic version that you pass on to either GAMS or in our case complementarity. So I think I'm just wondering whether there's some way that, because I think you guys certainly have a head start in sort of understanding how various MPSGE models can be translated into the algebraic version. I mean, that's sort of what we're fighting with right now, right? So we take one model, we try to figure out, okay, what is actually the algebraic thing that we need to generate? And it seems to be that a lot of that knowledge must actually be encoded in the Ruby code that you have. So I think we should probably see whether we can tap into that. I mean, it's good on one hand for us to go through that exercise and figuring that out ourselves, just so that we have it fully under control. But just having the Ruby as a template version also around would probably actually be helpful.
Yeah, I mean, I think your point about how to handle index codes, the guys at GAMS are masters at, and actually Ferris was the one that pushed them on this, they're masters at this translation of models from one format into another. Michael has all these things for extended mathematical programming. There's all these reformulation things you can do on GAMS models. And the one suspicion I have is whether or not the way we went was to keep the indexing through to the model, because that would make it easier to read. It's not so clear it's easier to read. And what's clear is that it's harder to write the code, right? It's a lot like, many times it sort of reminds me of building a boat inside of a bottle. You're trying to get everything. And so, whereas what they do is, what the GAMS guys do to translate from one system, they always just move to a scalar format. And they don't care about what, they just say, okay, the numbers are X1 through X 500,000, and we just write down the model. So that, I mean, that's what's happening in the background. And so that's the way they still are getting, they're relying on the function evaluator and GAMS to handle all the functions, but they don't try to index the model because they're not worried about whether the user can see it. So I don't know exactly what the answer is. I guess we stayed we stayed with the algebraic indexed version because I was very sensitive to this constraint that people want to see the code, but that's always the challenge, right? Is that this process of being able to see what's going on. That's one of the things that's sort of not so obvious to me what the best strategy will be.
Yeah. Yeah, I mean, so I came from the same intuition that, oh, if we keep the index notation, we can print it out. But I think the comment that we just had, right, that anything sort of more serious actually becomes so messy that maybe that's actually not actually, I mean, it's very nice for the toy model that I showed you.
Yeah.
But maybe that actually becomes less useful for large. That's a really good point. I can still see sort of benefits of sticking with this for the integration with the auxiliary things, because otherwise you have, so that I can see sort of a benefit there, that, but it's a point. I mean, thanks for pointing that out. I see that. I think we'll just try one. I mean, I think this is sort of how we're approaching this right now. Just, run, and then see where we stumble.
I'm very enthusiastic to the point that I don't have, I mean, we run a very lean ship here, so I don't have a lot of surplus resources, but I'm happy to go around and try to shake trees to get some resources to help you guys dig into this. It'd be great to give it like a 6-month heavy hit and see how far we get. And, because I think that the key, having a version of, the beauty is if you adopt the MPSGE syntax, we can still use GAMS for doing development work, and we end up with a model where you can see the MPSGE code, and we can have multiple different versions. But I think that from the standpoint of the users of WiNDC, which includes both the database and the library of models that goes with the database, having this in Julia, this would be a huge advantage, because that way, then not only is the data open source, but the tools are open source. This would be a really big advantage. So I'm keen on this going forward. So we have to think about how this works. Yeah. Are there any other
I mean,
questions?
this is, I think, the really exciting thing about the NREL thing as well, right? Because I think we're. So here's a prediction that I will certainly regret. But I think with a real push on the Julia MPSGE side, let's say, I don't know, 6 months, a year of really sort of heavy investment into that. And the NREL side, I think we could, within a year or two, we could be in a situation where there's a really quite functional, fully integrated, you don't have to deal with 10 different languages, version of this that is easy to access, all open. I mean, I think I see a path towards that. Let's just say that way.
The MPSGE code didn't, I mean, it's basically, the code's not really changed since 1990, but there was a period there between 82 and 90 where I was very intensively involved in doing modeling work with it and making innovative changes. So there'll be a period, my guess is you could get a functional version within a year, but then it'll take a couple of years of people using it and identifying issues that they'd like to be able to handle. And so that's the challenge going forward. I mean, but I think that putting getting to the point where we have canonical models up on the website, this would really be great. That'd be really great. And then what's the strength is the fact that you have the same solver means it's strictly a matter of can we write down the function. We know the thing is the key thing that's been the barrier in the past is how do you generate the Jacobians? And when MPSGE was developed, the GAMS function evaluator was not really competitive with my Fortran code. So when I came out with this thing, I could solve models 3 times faster than the GAMS function evaluator because my function evaluator is faster and more. It was specialized MPSGE stuff, and it could generate the Jacobian. And it has it uses a hashing routine for organizing the generation of the sparse matrix Jacobian is relatively, it's done with duct tape and chewing gum, but it works really fast. So, and the cool thing now is we have these languages that do this very fast. So all we have to do is generate it. So I think that the key elements are sitting there. So it's cool. We kind of, I don't know, in terms of people who tune to this channel to learn about how to solve national level models may find this a little bit, this discussion rather arcane, but so I'm open to other questions that people have about stuff. I don't know. The key thing is to get people who want to do stuff with passion, and what's clear is that David has some passion for doing this stuff. I see Max is there. Max has similar sort of enthusiasm for everything he does. He's really a big fan of Julia. So, yeah. Above all, let's have fun.
Do we have any questions relating to the household build that Andrew presented?
Yeah, this is John Becker. I've been looking through the WiNDC database a little bit too, and I'm curious if there was an intention about how labor and capital taxes sort of fit into all of this. I know there's sort of ways that we can do our own thing, but I'm also curious if there's something that's going to be built in or something into the benchmark. So thanks.
Great, John.
Yeah, I can respond. So in the household build, we will have labor and capital income taxes built in, but it will only be for at least initially only for a representative set of years. I think for the most recent years, 2015 to 2017, and that was sort of in order to do that. On the SOI side, we actually have the tax data because it's IRS data, but on the CPS side, we use the tax sim model.
Okay, thanks.
Yeah, great. So I guess if there are no other questions, I'd like to thank everyone for coming. Thank David for giving a talk. Andrew, your contributions are enormous. It's been great. And I guess in terms of what's coming up for WiNDC is we'll have the plan is to have sort of a 1-week summer school boot camp introduction to this. We're still sort of, these are ideas that just were coming out from this morning, but that'd be sometime this summer, July. Have a thing that we're introduced, focusing primarily on PhD students who'd like to learn how to use CG modeling. I'm hoping our new postdoc who's coming online, she has lots of good empirical chops, but try to help her learn a little bit about this stuff. So if you have students or any new employees at government agencies who'd like to learn about CG modeling, can count on something in July. And then the idea is to have a sort of WiNDC applications workshop sometime in September, October. I guess along with everyone else, where I'm kind of looking forward to looking past the pandemic. So I'm hoping we can have at least something that's the potential for we would certainly support remote participation, but I'd like to have that be in Madison if we could. It's hard at this point to predict, but the idea being the fall is really nice. September, October is my favorite time in Madison, so I think it might be fun to have an opportunity to get together. All things holding the same. And The other thing that we have is there's quite a bit of interest within the current funders as well as potential funders in integration of WiNDC into GTAP. And so the idea is we'd like to push that forward. And sort of an idea that came up this morning that I think would be kind of cool would be to have bi-weekly sessions where people who would like to listen in on what we're working on or maybe contribute to the exercise could jump in. We've had a lot of success with our connection with the USDA agricultural models through weekly seminars. We're sort of working seminars on that, and so we'll sort of formalize ideas about that and circulate them. So those are the three sort of initiatives we have going forward, and we're looking forward to having another year of interesting applications, and we're hoping that we can interest other groups in coming and participating in the stuff. So, yeah, we stand. So thanks everyone for coming along. I don't know.